Now let us see what is auxiliary circle and eccentric angle with reference to an ellipse. So let's consider some ellipse. We consider a horizontal ellipse here for understanding. Now I have shown this major axis of the ellipse, right? Okay. Now the auxiliary circle is that circle which is drawn by considering the major axis of the ellipse as the diameter. Okay. So if we consider the circle drawn as this, whose one diameter is the major axis of the ellipse, okay, then this circle is called as the auxiliary circle of the ellipse. Okay. Now moving on, let us understand what is the meaning of eccentric angle. So keep in mind the eccentric angle is defined for some point on the ellipse. Okay, so it is with reference to some point, say P, on the ellipse, and to find the eccentric angle, what do is we draw a perpendicular line to the major axis, and if we extend it, it will definitely cut the auxiliary circle also in some point. Let us call that point as Q. Okay. And we know that of course origin is the center of the ellipse, and of course it's the center of the auxiliary circle also. If we join O with Q like this, okay, the angle which that radius OQ makes with the positive x-axis, let us denote that angle as theta, and that angle is called as the eccentric angle of point P. Okay, remember that theta, the angle or the ray of that angle theta does not pass through P, it passes through Q, but the angle is still called as or defined as the eccentric angle for point P on the ellipse. Okay, so that is the auxiliary circle and eccentric angle. Now this is used in defining what is called as the parametric equations of an ellipse. So if we have some ellipse and we have a generic point on that ellipse, say P, x comma y. Okay. Now you know that the distance A is nothing but the semi major axis and distance B is the semi minor axis. Now in this case, if you observe the standard equation of the ellipse, that is x square upon a square plus y square upon b square equal to 1. Okay. And we know that theta is nothing but the eccentric angle of the point P that we have just seen. So if you observe, if we substitute x with a cos theta and y with b sin theta, then clearly both of these will satisfy the Cartesian equation of the ellipse. So therefore these are called as the parametric equations of the ellipse. Okay, that means each point on the ellipse can have the coordinates given by these two parametric equations, and these equations, as you can see, use the eccentric angle of that same point. Okay, so we have to remember the parametric equations of the ellipse as x equal to a cos theta and y equal to b sin theta. Let's solve one example based on this. Write the parametric equations of the ellipse given by x minus 2 the whole square upon 9 plus y plus 2 the whole square upon 25 equal to 1. Now if you look at the numerators of the two terms on left hand side, you will come to know that there is shift of origin that has been done. Okay. So nonetheless, if we consider that term as capital X and capital Y, right, the denominators are a square and b square in the standard equation we know. So therefore a square is 9, so hence we get a equal to 3, and since b square is 25, we get b as 5. And now the parametric equations are given by x is equal to a cos theta, but since there is a shift of origin, the capital X is nothing but small x minus 2, that is equal to a is 3, so we have 3 cos theta, and hence we get x is equal to 2 plus 3 cos theta. This is the first parametric equation about the x coordinate, and similarly we can write y is equal to b sin theta in the new system, but capital Y is nothing but small y plus 2 considering the shift of origin, and B is 5. So we have 5 sine theta, and hence finally we get y is equal to minus 2 plus 5 sine theta. So therefore we have got the two parametric equations of the given ellipse.